Hello to everyone. We are continuing our discussion on the use of double integrals for obtaining the volumes of solids. In our first lecture video, we used a double integral to evaluate the volume of a solid whose base is a rectangular region. So in this part of the lecture, we will consider bases which are not necessarily rectangular. So suppose that f is a function of x and y and it is continuous on a closed and bounded region R on the xy plane. The region R is not necessarily a rectangle. It can be a circle or an ellipse or any closed polygon. Now, what we do so that we can apply the methods that we had earlier is we enclose the region R by a rectangular region D given by the interval AB for x and CD for y. And then what we do is we define another function, big F, and big F is equal to small f if the point xy is inside the region R, and it is equal to 0 at points outside the region R, but still inside the region D. And then we can say that the double integral of f over r is defined by the double integral of big F over the region D. Now, are they the same? So firstly, the integral on the right, it makes sense because D is a rectangular region. And we already defined our iterated integral over a rectangular region. Secondly, it doesn't matter the size of the rectangle D that we use. It can be very large or it can have sides which are tangent to the boundaries of the region R. The important thing is the entire region R is inside the region D. And anyway, at points in the outside R, the function value of big F is 0. And so when you compute the integral using your subrectangles, the value of big F there is 0, so the contribution to the integral is also 0. And further, we can interpret the double integral of f over r as the volume of the solid that lies above r and under the surface z equals f of xy. Now, to set up the iterated integrals over general regions, we must first classify the regions as either of type 1 or type 2. Let's look at type 1 regions. We say that R is of type 1 if it lies between two continuous curves y equals g sub 1 of x and y equals g sub 2 of x. That is, R is the set of points where x is from a to b and y is between g sub 1 of x and g sub 2 of x. To illustrate this, we have the following figures. So the one on the left is very clear. We have two functions. So the upper function here is the g sub 2 of x and the lower function is the g sub 1 of x. And enclosed by x equals a and x equals b. So this region here is your R. Now it can also happen that you just have one function. Like in this case here, you just have one parabola. But we can still separate this into two functions. We have the upper branch of the parabola, that is your g sub 2, and the lower branch of the parabola is the g sub 1. It can also happen that you have an upper function and a lower function, but you don't know the interval for x, like in the third illustration here. So what we can say is that the interval for x is determined by the points of intersection of the two functions. So you have to determine where the two functions intersect, and from there you can specify the interval for x. Okay, now suppose that we have a region R, and we want to enclose it with a bigger region D. So the x interval is from A to B, but now the y interval is from C to D. The y interval from C to D can be partitioned into subintervals. So let's say we take a certain value of x here. So consider this a red line there. So you have your x value here. So you have a particular g sub 1 of x there and a g sub 2 of x here. So the interval from C to D can be partitioned as from C to g sub 1 of x, and then from g sub 1 of x to g sub 2 of x, and then from g sub 2 of x to D. Okay? And then we can define our big function f to be small function f whenever your point xy is inside the region and it is 0 outside the region. So here in the unshaded part of the rectangle. Take note that if your y is between c and g sub 1 of x, then you get a point which is outside the region R. Also, if your y is between g sub 1 of x, g sub 2 of x, and D, you get a point which is outside the region R. So the value of big F there is 0. On the other hand, if your y is between g sub 1 of x and g sub 2 of x, you get a point which lies in the region R. So the value of big F there is small f of x, y. So from here, we can set up our double integral. So the double integral of R, we define that to be the double integral of big F over D. And as iterated double integrals, it will be from A to B for the x values and from C to D for the y values. And take note that we can partition C to D as given earlier into C to G1 of x, and then G1 of x to G2 of x, and then G2 of x to D. So this iterated integral can be partitioned into a sum of 3 iterated integrals. Now take note that in the first iterated integral here, your y is in the interval from C to G1 of x. So the value of f there, big F there, is 0. So that makes the entire integral here 0. Going to the rightmost term, your y is between G2 of x and D. So again, that falls outside the region R, and the value of big F there is also 0. So this integral also becomes 0. And so we are left with the middle term, and that gives us the value of the double integral. Okay, so in this iterated integral on the right, the bound on x is a and b. The bounds for y, the lower limit will be the function below, and the upper limit is the function above. So we cite this as a theorem. So the double integral of f of xy dA over the region R, which is of type 1, is equal to the double integral given by the integral from a to b of the integral of g sub 1 of x to g sub 2 of x of f of xy dy dx. Now, for us to easily know what function to put as your lower limit and your upper limit, we can use vertical strips inside R. So if you use a vertical strip inside R, then the lower boundary of the vertical strip, so it must hit the lower function there, g sub 1 of x, this becomes the lower limit of your inner integral. The upper boundary of the vertical strip, which is now g sub 2 of x, becomes the upper limit of the inner integral. So let's have an example. Let's evaluate the value of this double integral of 2x minus y over the region R, where R is enclosed by these two parabolas. So take note that when you make a sketch, the region that we get is given by this figure here. So the lower curve is given by y equals x squared, and the upper curve is your x equals y squared. Okay? So to set up our double integral, we need lower and upper limits for the inner term. So since this is a type 1, we can use vertical strips. And the lower limit here would be y equals x squared, and the upper limit would be y equals what? Take note that the curve which is above the region, which covers the upper part, is x equals y squared. And from there, we solve for we solve for y, and we get y equals the square root of x. So there's a negative part, but the negative will be below the x-axis, so it will not be a boundary of the region that we want. So we only consider the positive square root y equals the square root of x. So your limits now will be from the lower function x squared to the upper function square root of x. What will be the bounds for x? So you just get the intersection of the two. So we equate the square root of x with x squared, and from there you will get x is 0 and 1. Okay, so to evaluate this, we first evaluate the inner integral with respect to y. So we get a 2xy minus y squared over 2 evaluated from x squared to the square root of x. When you substitute this with the square root of x and then later with x squared, we get this expression here. So this one uses the square root of x. This here uses this x squared. Simplifying, and then we integrate with respect to x. This is what we have. Evaluated from 0 to 1, we get 3 over 20. So the value of this double integral is 3 over 20. Another example. We have no more examples, so our examples now will come in the form of exercises. So I will give you some time to work on these exercises. You may pause the video as you try to answer these exercises. Okay, so now let us go to the solutions of these exercises. In the first lecture video, I left you with a set of exercises for evaluating iterated integrals. And then we will also look into the second set of exercises. So for the first set, evaluate the following iterated integrals. So here we work with the inner integral. So it is with respect to x. So we evaluate. So we get x squared over 2 evaluated when x is 0 and then when x is 2. And this is what we get there. And then for the outer integral, we will have to use integration by parts. Let u be equal to y and dv equals e to the y dy. Correction, this should be dy here, okay? So we get this expression there, and we have this expansion, and the answer is 2. Now for the second one, so we can integrate with respect to y first. Take note that we can put the x over x squared plus 1 outside because it is independent of y. So it is a constant in terms of y. And then integrating what's inside, we get this expression here, evaluated from -3 to 3. Then we integrate, we let u be x squared plus 1, and then we get 18 over 2 ln of x squared plus 1 as the antiderivative. And then we evaluate when x is 0 and when x is 1. And the answer is 9 ln of 2. And for our last, we have this. So we can let u be xy. So du is x dy. So that takes care of the x and the dy here. And then we change the limits. When y is 0, u is x times 0, or that is simply 0. When y is 1, we get u is x times 1, or that is simply x. So this iterated integral may be written in this form here. Evaluating the inner integral with respect to u, we get negative cosine u from 0 to x. So that gives us negative cosine x plus 1. And then we evaluate with respect to x now, we get negative sine x plus x from 0 to pi halves, and the final answer here is pi halves minus 1. For the second set, we want to find the volume of the solid under the plane 2x minus 3y plus z equals 6 and above this rectangle. So firstly, we have to establish that the function for the plane is indeed non-negative. So our f of xy is equal to z, and from the equation, z is equal to negative 2x plus 3y plus 6. So for x, the bound is negative 1 to 0. So if I get negative 2x, I have to multiply everything by negative 2. And the rule for multiplying by negative 2, the inequality changes directions. And then for the 3y, using this interval for the y, we multiply by 3. And we have this. And then we just get the sum, negative 2x plus 3y. So we just add up the lower bounds and the upper bounds. And then finally, we have a plus 6 there. So we add 6 everywhere. And we have this. And this is our function f of xy. And now it is greater than or equal to 0. So this shows our function is non-negative. Therefore, we can use the double iterated integrals to give us the volume of the solid. So dy dx, so the outer is for the x interval, the inner is for the y. So integrating with respect to y first, we get negative 2xy plus 3y squared over 2 plus 6y from negative 2 to 1. Evaluating, and then integrating now with respect to x, we get negative 3x squared plus 27 over 2x. Evaluated from negative 1 to 0, and that gives us the value of 33 over 2 cubic units. That is the volume of the given solid. For the next example, we want to find the volume of the solid under this curve and above the rectangular region R. So first we show that our f is greater than or equal to 0. So the bound on x is from 1 to 3. So we want the x squared, so we just square everything. The bound on y is negative 1 to 1. What happens when we square? Do we get a 1 to 1? No. What we get is y squared is from 0 to 1. So if we want a negative y squared, we just multiply by negative 1. The inequalities change directions. So therefore, x squared minus y squared is the same as x squared plus negative y squared. So we add the lower bounds and the upper bounds, and we get 0 to 9. And this proves that our function f is non-negative. So we can use the double iterated integral to give us the volume. And we integrate with respect to y first. And then evaluating from negative 1 to 1. And then integrating with respect to x, we get 2x cubed over 3 minus 2/3 x from 1 to 3. And what we get is 16 cubic units. Finally, we consider the last example. We want to find the volume of the solid in the first octant bounded by the cylinder 9 minus x squared, the planes x equals 0, or that is the yz plane, y equals 0, or that is the xz plane, and the plane y equals 2. So a sketch of the solid of the surface looks like this. Okay, so take note that this axis here is the x-axis, this is the y-axis. So this was plotted in MATLAB. And take note that your solid, your surface, will intersect the xy plane when x is equal to 3. And how do you get that? You just take note that the xy plane is z equals 0. So when z is 0, you just set 9 minus x squared equals 0, and that gives you x squared is 9, or x is plus or minus 3. Since we are considering only the first octant, x is positive there, so we take x is 3. Now this is the plane y equals 2. The plane x equals 0 is the yz plane. The plane y equals 0 is the xz plane. So the region that we want is bounded by this surface and these three parts of the plane, and also the base. So the iterated integral for the volume gives us, for the y is ranging from 0 to 2, and the x is ranging from 0 to 3. Okay, so evaluating the inside, we get 9 minus x squared times quantity times y. Y is from 0 to 2. And then evaluating that, we can put the 2 outside. And we have 9x minus x cubed over 3 from 0 to 3. That's the definite integral with respect to x. And this gives us the value of 36. So the volume is 36 cubic units. Okay. So that ends our discussion for today, and also the exercises. I hope that you were able to follow the solutions and make use of what we have learned.